Okay, today we are going to start with actually it's a continuation of yesterday's class because we sort of talk about how to calculate the energy density for different phases, right? And the example we were giving was like BCC 3D structure. But since in our tutorial session, first of all, you work on this 2D code. So just as the supplemental material, in the very beginning today, I'm going to actually show you the results of this phase diagram calculation of 2D PFC model. Because with all this information, you are going to actually reproduce the phase diagram construction for the 2D PFC model this afternoon. But aside from that, you can actually, by knowing where the phase boundary is, you can already start several simulation with proper parameter to explore the material problem that you are interested in, okay? So I'm not going through the details just to give you like a sort of table. So for example, for like 2D hexagonal structure, you are expecting the solid density for the hexagonal structure will be something like this, right? But most importantly is what is the structure should look like, or what is its corresponding one mode approximation, and that would be this one. Precise hexagonal structure, how do you get this form? It's by summation of those 6 plane waves. And here my choice is right here. You have K1, K2, K3, they are all 120 degrees apart. And those that K1, that's K2, that's by K3, that's right. And 4, 5, 6, they are just the conjugate factor from the previous 3. So you see the K4 is the negative K1, and the K5 is the K5 is here. K5 is the negative K2, and the K6 is negative K3. So of course you can have your own different choice. You probably can choose K1 is actually in my y-axis, and the solution is going to be slightly different. But if you do the summation of those 6 plane waves, that's the solution you are supposed to get. All right, and just plug in these insights for the density into this free energy, right? And do an integration over one unit cell, and the energy density should have the form like this. And again, you are seeing something that's similar with the BCC lattices, is that you have this non-finished A cube term here, right? And we talk about this term actually helps the hexagonal lattice and the BCC lattices to have a lower energy. So that's why usually in 2D, you are expecting to get this hexagonal lattice, and in 3D, you are expecting to get this BCC. And one more thing to note that is when you carry out this integral over space to get the energy density for the hexagonal lattices, right? It is not that easy to get like integration over hexagons, right? But actually, you don't need to do that. The only thing you need is actually a repeated structure, right? So what you are doing is actually can take this small rectangle, right? And since you know the form of this hexagonal density insights, so you exactly know if you want to have a repeated structure in the x direction, it has to be 4 pi, right? Because here you have this 1/2 x here. So in order to have this going to repeat itself, it has to go from 0 to 2 pi. So in order for this 1/2 x, the direction to become 2 pi, then x has to take the form of 4 pi. So that's why in the x direction, when you carry out the free energy calculation, the integration limit in the x direction should be from 0 to 4 pi. And the same thing happens for the y direction. So I'm giving you the result here. And due to there's a square root of 3 over here, and you are expecting here is a shorter dimension for your integral. All right, so something to think about in the afternoon. All right, so with all this calculation, you have the liquid density and the solid density, then you can do a common tangent construction, right? So this is also a result that you probably can double check in the afternoon. But what I'm going to show you here is that when you do the calculation, you are going to get several numbers and have all those phase boundaries determined. So here, just to show you one example, if I go along epsilon equal to 0.1, right, and I'm choosing different density like negative 0.18, that will be somewhere here, right, which will give me solid. Because the phase boundary is the phase boundary is at minus 0.1955, and minus 0.2061. So 0.18, 0.19, and 0.21, they are all outside the phase boundary. But you can see the first two, they are actually in the solid region, and the third one is in the liquid region. So when I play the movie, you are going to see the third one, the solid should disappear. And for those two, although you are expecting in the end you only have the solid phase or the hexagonal phase, but if you have a denser density, which means you are expecting you have more material, so you are expecting to have a faster solidification rate. So you are going to see that difference. Okay, so in my simulation, I basically have this long stripe because I want to study the solid-liquid interface or the solid solidification in one dimension, for example. I don't really care about what happened in the other direction. So I only prepare for like 1 or 2 unit cells here, but I prepare a really extended dimension in the X direction. All right. And initially, I prepare the crystal seed just like what we had shown in the previous slides. I just plug in exactly what is this form here and also use the proper amplitude, right? Okay. Okay, so we have the seed, and let's see the movie. So the third one, you already see the solid melt, right? And the first, on the top, you actually see this one actually solidify faster than the second one, right? So that makes sense. So here, just also an example showing that you can use the PFC to study the kinetics, right? You can see how fast the interface is moving, either it's melting or solidifying. Okay. All right. Something we else can do is actually now let's pick the density within the coexistent density. So you are expecting a phase separation, right? Because those two numbers are between the solid-liquid coexistence. But this is different, right? The lower one is actually has less particle. So what are you expecting if you are choosing the density somewhere, in the coexistent region, but the mean density is different? You are going to expect different fraction of the solid and liquid, right? According to the level rule, right? If you are very close to the liquid boundary, then you are expecting majority part of the system will be liquid. If you are close to the solid boundary, then almost your system you are expecting solid. So it depends on how close or where the parameter, the mean density you are choosing, then you are expecting different fractions occurring here. So let's play the movie here. It's actually running, so it's evolving. And since now, I think I only have like 512 points, so you roughly can see the solid fraction at the bottom simulation is a little bit less. But if I really prepare a very extended system, like 10 times larger the system, you can really see a significant difference showing up. All right. Okay. Right. So also make something that we would expect from the material to have this follow the level rule. Okay, the final movie I'm trying to show you here is if I move, I change different epsilon, right? Because for all those simulations, I'm setting epsilon equal to 0.1, but I can move around like changing the temperature, for example. So here you already see the solid-liquid coexistence because I'm choosing the mean density is also in between negative 0.26 and negative 0.29, right? It's in between. So I'm expecting to have a solid-liquid coexistence. But one thing I actually want to emphasize through this simulation is that if you look closely at the interface, the width of the interface, which means you have solid on one side and the other liquid, the amplitude should be 0. But for 0.1, the simulation, you will see a quite extended interface width, right? Start from solid and decay. If you can make out this figure roughly, it goes through maybe 6, 7 atomic planes. Even here, you still pick up some ordering. But when you increase epsilon to a higher value, now you only see maybe 3-4 layers, and it will start from solid, and the density will decay into a liquid. And that is something actually we are going to talk about today. Why the interfacial width is associated with the PFC parameter epsilon here. And that's also one important assumption that we are going to carry out this multi-scale analysis in today's class, all right? But before I move on to next lecture, is there any questions? Okay, today we're going to do two things, maybe 2+1. So mainly I'm going to talk about the physics of the phase field crystal model. So first is the classical density functional theory of freezing, and what is that, right? So the next thing is, once we have some physics introduced through the density functional theory of freezing, then we are actually expecting, for example, some physical rule has to be obeyed by the liquid and also by the solid, and those things should be always true regardless of your model. So your model should actually should realistically capture those physics in order to claim that's a valid model. So the physics we are going to talk about is the classical density functional theory of freezing, and based on that, we are going to construct a phenomenological model that's a Ginsburg-Lenoir theory. But in the end, you are going to find out that basically what we are going to do is just a multivariable phase field model, okay? Then we are going to make a connection, finally, how the PFC is connected with this classical density functional theory of freezing. And once we can make that connection, then there is a physical origin for this phase field crystal model. It's no longer a mathematical tool. It actually has some physics, right? Then that's something you can rely on to model the material behavior. Okay? All right. Then, if we have time, we probably can talk about how to set the proper value for epsilon and for different materials. Right? If, for example, you have BCC irons at melting temperature, so what value of epsilon should you use to model this BCC iron and liquid coexistence? Okay, all right. So the density function theory actually of freezing, it can trace back to as early as 1940, but people start to use that, try to answer the solid liquid property around 1980s. So there are a lot of important paper I'm listing here, like the Ramakrishnan and Yusuf paper is quite famous, that they actually use the density functional theory to successfully capture the solidification or the freezing behavior of hot sphere. And since 1980s, Akstoby and Heyman made a lot of progress, also used the DFT to study the solid liquid interfaces. So the idea of this so-called density functional theory is something you can think of is that atomistically, right? You have a many particle system. You have so many particles, you have n particles, then you have to track their positions and the momentum. So there's a lot of degree of freedom, right? You have 6n degrees of freedom to track all the time. So maybe a simple way to describe the system is that using statistical mechanics and trying to reduce all those degree of freedom to a field, to a density field. Like statistically, what would be the probability to find a particle in certain space, right? So using that description, you are moving from a discrete atomicity description to a continuous picture. But once you have those density field, then you know what's going on for your system, then you've got a nice description for this solid or liquid or solid liquid interface. So it is just a change of perspective to start with something discrete, right? You have a Hamiltonian for this n-particle system, and basically it's composed of the kinetic energy and the potential energy. But you can next using different ensemble of your choice. If you like it, you can use the canonical ensemble, or you can use the grand canonical ensemble to write down the partition function and do a statistics. In the end, you can get the free energy of your system and write that in terms of what's the density field of that. So I will not go through all the details, but through the concept I just described, the classical density functional theory eventually will give give you something like this, right? The total free energy of system is a functional of the density profile, of course. That's the whole point. So if you give me a density profile, I just plug in whatever the functional form is, it's going to give me a value. So the system is going to favor which density profile that will minimize the energy, minimize the free energy, right? So this kind of free energy can be separated into two terms, I mean physically, right? One is the ideal term, which means if there's no interaction in the system, so it's like an ideal gas. So you are expecting if there's no interaction, you should only recover the ideal part. But the interesting thing is that the material science is so interesting because there are interaction between particles, right? Between atoms. So because of this interaction, you are expecting to have extra term. That's basically the free energy contributed from the interaction, right? So just intuitively, you should have at least those two contributions. Then the ideal part is similar to the ideal gas, right? You have this rho log rho minus rho. It's something you can look up in the text, and you always find this kind of like n log n or log n factorial things. You can do it in expansion. So that is not really a surprise. And the lambda here is the de Broglie thermal wavelengths. So that's usually coming from the kinetic energy if you do the partition function. But regardless of that, the rest is just the typical ideal gas term. Okay, but we are expecting to have interactions. So this kind of interaction, what we can do usually is that we can do a Taylor expansion, sort of functional Taylor expansion around a fixed value. And usually the reason we are doing that is we are trying to write a free energy, right? And the end goal is to actually minimize this energy. But what we are trying to do actually is to minimize this energy with respect to some reference state. And usually that is the liquid state. So which means if I have a liquid, but the liquid now there's interaction between particles, right? So if there are some perturbations or some noise to the liquid, there's going to be some structure occurring. So the question we are trying to answer is that if there is interaction and if there are disturbance in the density, what would be the density fluctuations that minimize this energy, right? So we don't really have to write down the whole thing for the free energy. We only have to say relative to a very boring homogeneous liquid state, which is the density just a constant rho naught. So since I'm subtracting that constant, whatever increase or decrease due to the density fluctuation, that will give rise to actually the free energy changes, right? So always you can just do a expansion around some reference state, and that state usually is a liquid state, right? So the classical density function theory here is we are trying to write down the free energy functional, you can say, for an inhomogeneous liquid, which means we still consider it as a liquid. But now the structure can emerge. Maybe it's due to the interaction. And if the structure emerge, what kind of structure will emerge and how that structure will lower the energy? That's the question we are looking for. All right, so this step is just saying, okay, I can do a functional Taylor expansion around a fixed value, so this is just a constant. So the rest of the formulation is just like a Taylor expansion, right? You are taking the derivative with respect to the function, so that's the functional derivative, and times how far away the density is changing from that rho naught. So you are expecting an infinite term in this expansion, right? Just like the usual Taylor expansion. But if now the fluctuation of the liquid is small enough, then I can basically truncate this infinite series. So there's an assumption for this density functional theory of freezing is that we are looking at a structured liquid. But the structure, although it's inhomogeneous, but that fluctuation is not really large, right? So in the end, we are consider that kind of structured liquid as our solid. So the density function theory is solving a really homogeneous liquid state in contact with the other inhomogeneous liquid. And we are taking that inhomogeneous liquid as our solid. And the reason of doing that is that simplify our calculation. And back in 1980s, people don't do that. They just plug in everything. And they might truncate the correlation function to a certain degree because it still takes a lot of computation power. But purpose of introducing the density function theory today is to make connection with PFC. And as you have seen in the PFC simulation, the solid basically is very like, it's basically one mode approximation, right? It's not a really localized structure. So that somehow sort of justify, we can just truncate the Ted expansion to a certain degree. Basically, we just take the truncation after n is larger than 3, then we throw everything out. Okay, so since this F is the contribution for this energy from interaction. So you are expecting this term is associated with the potential here, right? If there is no interparticle potential, then you don't expect to get this term. You only have something like ideal gas. So this term is associated with something you probably already know, is the correlation function, right? So let me just use the short notation like the rho of R minus rho naught is the delta rho. And this functional derivative is associated with the correlation function because the correlation function is associated with the interaction. If there's no interaction, there's no correlation. All right. Okay. So here we just define the correlation function is the functional derivative with respect to the density profile. Okay, you will probably get this KBT somewhere. If you plug in, they cancel out, so it doesn't matter. It's just trying to justify the energy in F and then the energy here cancel out. So just how you define the correlation function, and that doesn't really matter. So before we make things too complicated, just recap what we are having here is that we start with a really boring thing, liquid, and we know how to write down the energy. And now we just want to perturb the liquid a little bit because there's interaction. So there's an interaction term adding on to the free energy, and that's it. The concept is as simple as that. All right. All right. So we only want to know the free energy difference relative to that reference state, which is rho liquid or rho naught. So you can just subtract that from rho naught. So I only show the results here. So here you got free energy, but after subtraction, you got this change in the Helmholtz free energy. And I divide KBT to the left-hand side, so you get something like this, right? So you can still see the structure. There's a rho log rho minus rho, but because now I'm subtracting the contribution also from the homogeneous liquid, so that's why you have this rho naught here. So you can verify just by doing a simple subtraction, you should have the first term. And the second term only from the interaction, so you just copy everything we have here and right. I mean, we of course the derivative we subtract this homogeneous term, so we just drop the contribution from this F rho naught. That's it. Okay. So we are not doing very much here. Just to show you that you have two contributions to your free energy. One is because there's no interaction, and once there's an interaction, you should account for that. All right. Okay, so let's make some space. All right. Yep. Sorry. Yes, that's the potential you have in the Hamiltonian, right? If you have a particle they are separating in certain direction, that's the pairwise potential I'm using here. I mean, I'm going to assume it's a pairwise potential because that's going to simplify the calculation. But that's the potential between particles, between atoms. Yeah. So there are some approximation you can do theoretically, just to simply relate the potential here with C. But we are not going to do that because usually you can also get C just by running an MD simulation. So, I mean, but if you just want to do everything theoretically, you can do certain approximation using the Mayer expansion, keep track to a certain degree. But some approximation are very nice, actually. Okay, so here we'll only keep the lowest order expansion, and of course it is the interaction, so the lowest order term involves two particles, right? Because you need two particles in order to have interaction. So we don't have, we dropped it like 3-particle correlation and 4-particle correlation, something like that. We want to keep the lowest order term, all right? And I further assume it's a pairwise potential, so that's why the C2, the correlation function, only depends on the distance but not the direction, all right? Okay, so now what we're going to do is just to simplify the expression, because there's a log term here, so if you, the log term is a nonlinear term, and we just want to get some physics, so we want to truncate the log to a certain degree. So again, we are looking a system of an inhomogeneous liquid, which means the density fluctuation is not that large compared to rho naught, all right? So if delta rho is much less than rho naught, I can expand the log rho of R over rho naught, right? So what I'm doing here is just to deal with this ideal part only. So this rho of R, I can write that as rho naught plus delta rho. And rho of R divided by rho naught, that gives me 1 plus delta rho divided by rho naught, right? Okay, and minus delta rho is after here. And since delta rho over rho naught is a small number, so log 1 plus x, if x is small enough, that approximately is x minus 1/2 x squared and plus some higher order terms, right? So that's what we do, just expanded this log. I got this one. But immediately you will see that you have terms like rho naught times this term, right? So that will give me a delta rho, cancel out with the last term. And other than that, the lowest order will be the quadratic order of delta rho. So immediately you will get the leading order term is proportional to the delta rho squared. So in the ideal part, the leading order is proportional to delta rho squared, and also for the correlation or interaction is also a quadratic order, and which makes sense because in the end you want to minimize the free energy, right? So the functional derivative with respect to delta rho should be 0. You shouldn't see that effect. I mean, if you like to solve the equilibrium property. All right. Okay. So next thing is that we want to deal with the correlation, and since we only have C2, right? We have the superscript 2. So I just don't bother to write the 2 every time. I just call this correlation function capital C of R, and that's it. I didn't do anything else. So I just simplify this ideal part to which is 1/2 delta rho squared here, and divide by rho naught. And that's it. And I just copy everything we had this for correlation function, but change the notation a bit and plug in here. Okay, so if that's my free energy functional, and if I can do, of course we can do. I mean, if we minimize this free energy, it's going to tells me something, that is, if I have density perturbation fluctuation somewhere, like in the origin, what will be the profile looks like due to this perturbation? All right, so that's basically the physics behind that. And the profile has to follow only one rule, is that that profile is going to minimize this free energy difference, and that's it. So there is only certain profile, only one profile that will give you the minima of this delta F, and that's your solution. Okay, so once again, let me recap the physics here, is that we are constructing a free energy for inhomogeneous liquid. So since it is inhomogeneous liquid because there's interaction, now we end up with this kind of energy functional that will tells us what kind of density fluctuation or perturbation or distribution in space is going to minimize the free energy. So that's the profile that's going to be preferred. So how does that related to the solid-liquid interface. So if I have a solid, right? So I already have some energy being perturbed, some periodic structure. But there's a liquid nearby. So since I already have some perturbed profile already, this energy is going to tell me how the density is going to affect the unperturbed liquid. So by minimizing this, I can find out what is delta rho of R. So that's going to give me a very realistic density fluctuation profile, right? And why the liquid has structure? Because it's subject to the influence of nearby solid. So you already have some hint saying there's a huge density peaks here. This is some structure. Then this energy is going to tell you how the density is going to relax into liquid, and that's very, very realistic. So if you your work is associated, or you know how to do MD simulation, you can actually look closely to the solid-liquid interface. So if you can find a way to trace the ordering starting from the solid side and how that decays into liquid, and that profile should be exactly follow the prediction of this density functional theory of freezing. Okay. All right. So that's basically something I only want to talk about, the density functional theory of freezing. Okay, so that's the only physics we are trying to capture here. So with that input, we can construct a Ginzburg-Landau theory or a phase field model to implement all this realistic physics, right? And see how well we can do to reproduce the property of the solid-liquid interface. So that's the result we have done in 2006. So if you would like to get more detail, you can check out our paper. So the starting point is actually what we have here, but we still have some work to do to simplify that to what you are used to, like phase field model, like free energy for that, right? Because if you recall what you have in the phase field, you would have not only the quadratic term, right? The phase field phi usually have this double well potential, so you are expecting at least a quartic order polynomial just for the potential. But here we only have a quadratic order, so that's something missing. And also you are expecting a square gradient term, right? The inner energy should be some positive coefficient times the gradient phi, the whole thing square. But it looks nothing like a square gradient term yet. So what we are going to do for the Ginzburg-Landau theory, we are going to do a little trick on the correlation function term to make that, to reduce that, to simplify, to expand that term. So in the end, you are going to see that this term will give us a square gradient contribution. All right, so we want to construct a Ginzburg-Landau theory, and a good theory should capture a realistic physics. So the goal is trying to get a Ginzburg-Landau theory that basically have all those terms in contact. You mean here? Yeah. So it's a double integral. So we are summing over all kinds of possible distribution, and there's a and C is also a function of their distance, right? So and C we can get from C basically is how the local delta rho is correlated with others. So basically we are summing all kind of energy contribution. Yep. Okay, let's see. Okay, so we are going to formulate a phenomenological Ginzburg-Landau theory particularly for the solid liquid system. So first, what would be the order parameter for the phase field or for Ginzburg-Landau theory here, right? Since we are describing something like a solid liquid interface, and the delta rho is actually the density variation over here. So the order parameter that distinguishes the solid phase and the liquid phase is actually the amplitude of this oscillation, right? If the amplitude does not equal to 0, then that picks up some oscillating field, that would be our solid. But if the amplitude equal to 0, and that should be the liquid, right? So we would like to use the amplitude of the density oscillation or the envelope of that as our order parameter. So the rho, we can write that as rho naught times 1 plus summation. Again, here is the depends on the structure of the solid we are talking about. You can use the different set of reciprocal lattice vector. All right, that's the centric as we show in PFC. And according to our previous definition, the delta rho is the fluctuation away from rho naught. So that will be just the second part, rho naught times the summation of all the plane wave. Okay. All right. Now we want to know how the density profile is going to decay from the solid side to the liquid side. So basically it's like also the same question in phase field. How do you go from one state to the other state, how the profile changes? Because the detail of how the profile changes will give rise to different energy, different surface energy, right? So that's how you implement this surface energy anisotropy in the phase field. All right. So in that case, that's a simplify our problem saying let's only look at the planar interface along the z direction. So what you can have is actually a BCC liquid interface, and I'm defining the direction of the interface normal as my z direction. But everything in XY is just a planar structure, right? So nothing changes with it. I mean, except that the density will pick up the periodicity, but its envelope only varies from the solid is some constant, and of course the interface decay in liquid will be 0. All right, so because we have that assumption, that's why the amplitude here only depends on z, right? So it's a planar interface we're talking about. So let's work on this correlation term, right? We are trying to make some approximation, so this one will look like a square gradient term that we have in the phase field model. So this only works if the interface width is quite diffusive, which means I'm requiring that the interface width here is large. All right, should be very diffusive. All right, so for diffusive interface, we can do a Taylor expansion of the delta rho r prime here, right? I can expand this delta rho of r prime, but I'm expanding this function around r. So here is basically r prime, but I'm expanding that around, from r, right? So here just z. Oh, that's right. Yeah, so I'm basically expanding this a of z, right? A of z prime around z. That's where I made my Taylor expansion. So you are seeing here, I'm just expanding, since it is r prime, here should be like z prime, right? So I'm expanding that around z, and z will be the same thing as this r. So what we are doing here is that for this pericolis function, when we calculate the energy contribution, we always need the particle density variation of 2 points. One located at r, the other is r prime. But those two have some relation, right? Because the delta rho is just a function of space. So for any function of space, or for any function of space, you can say there's a relation between this point and that point through a Taylor expansion, right? That's something you can always do. So that's what we do here. All right. So the reason we require that the interface has to be diffusive in order to truncate that Taylor expansion to the second order is that the dA over dz, which means the slope, right? How fast the shape is changing over z direction. So if that envelope or amplitude is just changing very slowly over the space, the higher order derivative will vanish quickly, right? So if you have a rather diffusive interface, then you can truncate that Taylor expansion to the quadratic order, because the first two terms they are going to the second term here, the linear term, is going to vanish, but you also need the second term actually to describe spatial relation between 2 points. So that's the lowest order you should retain, but we are going to see that detail later. Okay, so here we just do a Taylor expansion of this delta rho of r prime around z. Okay, we're going to do a little bit manipulation of the algebra. We have to do that in order to really see how this is connected to the phase field-like structure, right? So there are 3 terms here, so we should plug in 3 terms in back to this delta rho prime and carry out this integral. But that's going to be very tedious. So let's just do that term by term. So first, let us just plug in the first term, az, and to here. So we are not expecting anything special because it is a double integral over r and r prime. But once we plug in the first term here, the r prime dependence is only here, right? So it should not be a very challenging integration to do. So let's just work that out. So I just plug in that first term rho naught times a times exponential back to this integral, right? So I have the structure of double integral dr prime, and I'm picking up this rho naught squared because delta rho, I have 2 delta rho product here. They all have this rho naught prefactor here. So the amplitude is actually dimensionless. It's really just represent how big and how small is the variation, but without any dimension. And the rest of stuff you can see, the first term is just from the delta rho here, right? The first delta rho is just plug in this summation k, and the second one you just have this aj times. So basically, those are just the delta rho squared, exactly the same thing. All right, but this is just delta rho. Okay, and times what? Times this correlation function. All right. So something that we can use to simplify this expression is that we know if we just do a Fourier transformation of this correlation function, we can get its reciprocal representation, right? So that's by definition. If you have something oscillating in space, that's C of R, you can also use the same degree of freedom to describe that in the Fourier space. That's the same thing. But by doing so, you are actually getting something very nice we are going to show later. So how do we employ this function to facilitate our calculation next? Just do a simple comparison. You can change the variable we are integrating, right? So I can say instead of doing the r prime integration, I can just actually making r the place of first particle as my origin, and from there I'm still integrating all the space, right? So anyway, this r and r prime, they are all integrated all over the whole space. So I can just choose my own proper integration variable. I can still do a integration for the whole space. So here I just change the second integral variable to r prime minus r, and somehow you can combine that double summation. So you have this some k and some ki and kj, let's say, right? In this I and aj, I can write them together. And in order to have something I can use from this ck, since I'm having this variable as like r prime minus r, so I want to construct something like r prime minus r over here, right? So that's what I did here. So the trick is I can combine those two exponential factors into those two new things. But you can see here I have the exponential I kj dot r prime minus r. But in the very beginning, for kj, I only have r prime, right? So I actually adding one term more, that is exponential minus ikj dot r. So if I'm adding something extra, I have to subtract that later. So you can see here I have this negative ikjr, but here immediately I have this positive ikjr. So I'm not doing anything. I'm just adding one term and putting the other term, subtract that later. And the remaining is just what we had before. You see here exponential ik dot r. That's exactly the rest of it. So I didn't do anything. I just rearranged things. But now you can see I have exactly the same structure. That is my dr, and that is my cr, right? And that's my exponential ikr. And although there's a minus sign here, but since I know the correlation function in Fourier space doesn't depend on the orientation, so plus k minus k should have the same result. So those three things will give me this. So ck I'm getting here, so I'm not going to write those three things because I have to carry out the integration. And rho naught squared become a single row because the definition for CK, I absorbed one extra rho naught here. All right, and I just copy the rest of stuff. Like I still have to integrate over the space like R, right? And double summation, I copy from here. And I have like AI, AJ, they are all function of Z, but not Z prime, because we get that from the Taylor expansion. And also this nice exponential I times I plus Kj dot R times CK. That's it. And actually, that's one of the results we are getting here, because we are not going to further simplify this relation, but because there is this exponential I times this Ki plus Kj combination, and dot R to integrate that over the space. So as we just discussed a little bit yesterday, is that if Ki plus Kj, but what is Ki and Kj here is that they are all the reciprocal lattice factor for the crystal structure you would like to discuss in your solid liquid system. So now you're just picking randomly two of the reciprocal lattice factor. And in some case, in most of the cases, they will not be zero. If the summation of those two reciprocal lattice factors, they are not zero, the summation is not zero, then you are doing the integration over a larger space. For certain periodicity, they are going to cancel out because it is still an oscillating function. Yeah, so some of them are canceled out. So for example, I have a really large space, right? And I know for that certain combination, Ki and Kj, they probably will go like 1/10 of the system is going to be canceled out. Or let's say 1 unit of some arbitrary unit of space is going to cancel out. But my whole space is only like 11.2 space. So for the first 11 even size, the plus minus contribution is going to cancel out. But only for the rest, very tiny part, is going to have some contribution. But when I calculate the density, I have to divide by the volume at all, right? So actually, if the summation, the sum of the wave factor, when you add those two things up, if the sum does not equal to 0, the contribution is going to be very, very small because that oscillating nature, right? So when we carried out this integral, the only thing that we need to take into account is only the mode where the Ki plus Kj is exactly equal to 0. So that exponential things I can rewrite as a Kronecker delta function, because only when Ki plus Kj equal to 0, and this gives me 1. Otherwise, that would be 0. There's no contribution. So that's the only simplification I'm working on here. So that's it. So we have already taken care of the first term. We're not doing anything else. So immediately you can get some other nice result is that, oh, through this trick, we can also work out this delta rho square, right? Because this delta rho square is just the same thing. We're doing the double sum, and there are two A product, and it's also like different because they are all function of R. So we are exactly getting this kind of structure, right? One is I times Ki dot R, the other is exponential I Kj dot R. So even without doing any calculation, I can say, this term will exactly have the same structure. The only thing different, there will be a C of K coming out because there's correlation for the previous term. But here, just a simple coefficient 1/2, and that's it, right? So although we are talking about simplification of the second term, the correlation term, but through this calculation, we can also reduce a little bit the ideal contribution as well. So I can combine those two things. So what we're simplifying is the ideal part plus the first term in my expansion for the interaction part. Their contribution basically is what? I have this 1 over 2 here and times the rho naught refractor. And I have the structure saying that Ki has to be Kj. So they are the same. I have to equal to minus j. They are common quantity. So I have this AI squared. That's it. And instead of doing a double sum, because Ki plus Kj has to be 0, so it becomes a single sum. Right? And here I just combine the coefficient 1 from here, and here's minus k from here. That's it. And this 1 minus c of k, is associated with the structure factor of the liquid. So if you have experience with MD modeling the liquid or solid liquid, you probably know pretty much everything about the structure factor. So that's something you can get easily from MD. Right. So we are associated with something that we can first carry out MD simulation, and you can get certain value, and it's going to be used in the dismal theory I'm going to show you later. Okay, so that's something let me see. Okay, so we have already taken care of those two green parts, right? So listen, I just rewrite that. Right? I combine those two terms, the factor become 1 over s. So I just write that results here, right? You see this single summation 1 over s times ai squared. Okay, and the second term is going to be 0, right? And the reason is being that it's an odd function, right? Z prime minus z could be positive and negative, right? So the integration, the idea is that I'm taking R as the center of my integration, and I'm integrating over the relative distance, R minus R prime, over the space. So there's always a symmetric contribution from a positive and negative pair of Z prime minus Z, and there will be the other part that will give you a negative value. So after the integration, you know the contribution they are going to cancel out. So you can really reproduce the calculation, but in the end, you are going to see that contribution will be 0. Okay, so that only leaves the last term. We only need to work out. That will be the second derivative of a with respect to z, but there is something z prime minus z squared appearing. So we are going to deal with that. Yeah, I mean you mean including the higher order correlation, or yeah? That's a very good question. I think probably both. Right? And here we didn't even consider higher order correlation function. And the reason we are dropping out the higher order derivative is that it's going to be very small coefficient. So it depends on how anisotropic the material we are talking about. If it's diffusive, then there's a justification we don't have to worry about those things. But if we want to model something really anisotropic, then I think we need to include that, which means a rather sharp interface. Right? And that's I'm not so sure. Okay, that's something to think about. So I think that's actually the point, introducing this work in detail. So we know what's the truncation, what the assumption we are making, with what we are simplifying, basically. Right. Right. So let's look at the next term, right? So we are doing something similar to, so plugging everything back. So I have this negative 1/2 here, and the rho naught square coming from this delta rho square, right? So that's fine. Double sum is also here. And the first delta rho is simply summation k ak exponential I k I dot r. But the second term is coming from the blue parts, right? So I have this 1/2 factor here, and the second derivative of a with respect to z, and also z prime minus z squared. And you have exponential ikj dot r prime. That's it, and plugging this c of r in the end. Okay. So it doesn't really look like this ck, right? Because the problem now I have this extra z prime minus z whole thing squared, but that doesn't seem to be really difficult thing to resolve. So what we can do is the same thing. It's just to change the integration variable the same way. And the reason of doing that, of course, we are trying to make out what's the argument of these correlation functions. So we do that on purpose, no problem. And we also recombine the exponential ikj, I dot r in the same way. So we know we are trying to make this term sort of related to ck, But because of this extra z prime minus z squared, we still have to do a little bit extra work, right, to connect this expression to ck. That's it. And the connection is quite straightforward. Basically, already immediately show the result here is that if you look at this dr, right? That's my dr here. I have c of r here, which is the second term. I also have the proper exponential term here. How do I deal with this extra term? Basically, what I can do is I can take derivative of this ck with respect to k, right? So every time I do that, I would make this this term. I will get one extra minus ir. R is the coordinate. So the way I can recover this coordinate being dropped in front is actually by taking derivative of c with respect to k. Every time I do that, I will get the spatial information dropping out, which is this z, but not completely. Your r includes x, y, z. Right? So a little bit detail I show above is that it could be easier to actually see that if I only take this ck with respect to the component, the z component of the wave number. So you can write this as kx, x, ky, y, kz, z. So if I only take the z component, take the derivative with respect to the z component, I only recover iz, right? So that's why I don't have x and y. But how do I associate this one back to dk, not dkz? Because I can do a simple chain rule, right? So EC over dk, I can just use a simple chain rule just to multiply one extra factor dkz over dk. But k and the kz just have a very simple projection result. So this factor is just k dot z, the inner product. That's a cosine. So here's the k hat dot z hat. All right, so the z is the interface normal. Right? Okay, so basically that's why you need the second derivative here. So that will give you this z minus z, the whole thing squared. And because of this negative I thing, square of that, so the minus side disappears. Right? So that's the only trick we need to do. But here now you see that that's part of our free energy, right? So we are adding something that's the second derivative times a, but not quite like what we have for the phase field. So a typical trick is to do an integration by parts, right? So you have a boundary term, and also the rest term will be a squared gradient squared, dA dz squared. But the boundary term you can drop out using the proper boundary condition, or just saying it's a periodic boundary condition. So now you are expecting a square gradient contribution in the free energy, and that's something you are quite familiar with, right? That's the term you are expecting in phase field methodology. Right? So you have a square gradient contribution, but you might worry a little bit about the sign, because usually in the phase field, this term is going to penalize the interface change. Going too fast, right? But you are seeing the sign is negative here. But don't worry about that, because the C double prime is always negative. So the whole coefficient is positive, right? Right. So now you probably can start to make a connection with something you are familiar with, that's the phase field model. But we're not quite yet to get the focus line of theory. And of course, although we have the interface term, the bulk energy is still not right, because you only have something like A squared, right? So you need something at least to the cortical power to have like that double L potential in order to have the complete theory. And that's something we are going to do next. All right, right. So we still need a quartic term and a cubic term in order to complete the theory. But before I move on to that, any questions so far? All right. Okay. So before we move on to this, how to properly formulate the bulk energy, just show you one example. This MD simulation result, the BCC iron using the MSA squared potential, and that's a structural factor you are expecting to get at a melting temperature. So just to give you a feeling that all the coefficient here is just a number. You can get it from this MD simulation, like S of Ki. So that's S of K. Basically, just talk about the value at the residual electric, the principal residual electric factor. That would be the peak of that. That would be roughly 3. And the C double prime K, you can also associate with, because we know S of K and the C of K has this simple relation to take a second derivative on that. So you're getting this minus 10.4 angstrom squared. So that's what I was saying. What I was saying about this term is possible, right? So that still gives this energy penalty if you have the interface that goes too sharp. All right. So we take a quick break, like 5 minutes, and we will continue. Now it's like 12:10 or something. So let's take a 5 minutes. So let me know if you have any questions. I'll be happy to. K-Max, yeah. Because they have this relation. So inverse that and plus this negative sign will give you some voltage inverted. Yeah, so we can do that for other material. Oh, okay. Yeah, that's right. That's right. I mean, later we're going to show the complete theory. It will be fun to see what happens for other material. Okay, those two numbers and whether we got the NSRP prediction right. Let's do simple theory. All right. Let's resume. Okay, so before I move on, I would like to emphasize something important is that although the formulation we know the end goal is to get something like phase field or instrumental theory, but immediately you can see something that's quite distinct from the current derivation. Is that the square gradient coefficient here, right? It's no longer constant. It actually depends on the interface direction, and it depends on its inner product of the interface normal and also the individual distributed electric vector. So just give yourself an example. For example, like if you have a BCC lattices, right? Let's say the interface normal we are choosing like 100, very easily. But K could be like 110, 011, etc. Immediately you will get the different inner product just for different K. So summation here means that we're expecting 12 terms. But even for those 12 terms, some of them will have the same coefficient, some of them will have different coefficients. And that coefficient will change with the interface normal we are choosing. Right? We'll just pick an example like 100, but how about for like 110, right? Or something else. So it basically because of this kind of orientation dependent coefficients, that's eventually leads up to the interfacial energy NSRP. So that's the connection we are going to make today. All right. Okay, so our remaining thing is just one thing is how to get a reasonable cubic and quartic term into the theory. And it's quite trivial actually because the only constraint is that we need a double potential for the solid liquid to be coexistent with each other. So here, just quickly summarize what we have so far, but there's no cubic term and quartic term. So the potential parts, we should have those two unknown, right? But those two unknown, basically, through the derivation we are having here, we know those terms could coming from like the expansion of rho log rho. So we only keep to the quadratic term. But there's a cubic term and quartic term with different coefficient, etc. But we are not going to use those coefficients because it's not going to give us a double well because we truncate everything. But now we only need few simple terms that give us a feature of double well potential. Right? So, but we know the structure of this cubic term or the quartic term would have something like also a quantum delta function times the product of those entities. Why is that? Because I would assume the cubic term contribution will coming from something like delta rho to the cube with some coefficient that's unknown, right? Because that's if we truncate the correlation function to the second order, the only thing left with us is only the bulk term. So if the contribution only comes from the bulk term, which means it can only come in from the delta rho to the cube power for the cubic contribution, and the quartic term only from the delta rho to the fourth power. And if you do a delta rho cube integral, you encounter again all this exponential I, ki plus kj plus kk dot r thing, right? So that gives rise to this quantum delta. And because it's triple product, you are expecting the product of 3 A's. That's it. All right. But here I'm not just using certain coefficient because A3, that's something we don't know. And I also introduced something new called the CIJL. That's not the, so what I want to say is that the cubic term coming from delta rho cube doing the integration, and the quartic term similarly from the delta rho to the fourth power cube. All right. But what is the CIJL or the CIJLM? Oh, I'm missing an M here. Let me fix that later. So those two things are different. Sorry. Here should be like the CIJLM. There are 4 indexes. Right. Okay. So A3 and A4, they are something we don't know yet, but we are going to fix that with the constraint of a double well potential, and one minimum at the liquid, A equals 0, and one minimum at the solid, when we know the solid amplitude, right? So let's not worry about A3 and A4, those two coefficients. But let's talk about what's the CIJL or what's the CIJLM here, all right? All right. So that's just a normalization constant which will simplify our calculation later. It's nothing but what? But just saying how many combination there is, and we normalize by these constants, right? So for example, how many combination I can have if I consider BCC lattice. So I'm worried about if I just picking those 12 orbital lattice vectors trying to combine, how many combination I can have to form like closed triangle in a reciprocal space. So the answer is 48, something we derived yesterday, or talk about, we really derive it. So if that's 48, then CIJL in that case will be 1 over 48. And that's it. So which makes that I sum everything. How many terms I'm having here divided by that number, so sort of like no normalization constant. And of course, you don't have to do that. Just simplify my calculation. All right, so the same thing. The coefficient here, CIJLM, also is defined as a normalization constant. That's how many parallelogram you can have that's form a closed parallelogram in the reciprocal space. I think depends on structure. It could be quite large. But I'm going to give you the example of hexagonal lattice later. All right. So for BC, that's right. CIJL is 1 over 48. Okay. So how do we get A3 and A4? Right. So the constraint is that's the proposed bulk energy, right? That's the proposed bulk energy. But A3 we don't know. A4 we don't know. C we can know if you give me the lattice structure. That's something easy to compute. It's just a number. So the only 2 things we don't know is the A's, right? A3 and A4. So we can write down the energy just for the bulk, like bulk liquid and bulk solid. And that's really trivial because in bulk liquid, A just equal to 0. So if you plug in that, give me 0. But for bulk solid, AI, AJ, whatever A1 to A12 for BCC, they are all the same. They are all the same value. Let's just put that A. So if I only talk about a bulk phase, not an interface, just a bulk phase, its energy is just the integration of the volume, right? Because everything doesn't depend on space. It's just some amplitude, A here. So what we are having here would be volume times this 1 over S of K we got here, and amplitude square, right? But how can we have this one extra 1 over Cij? And the Cij is defined the same way, try to normalize this kind of counting. And because for different crystal structure, for example, for BCC, this summation goes from 1 to 12, right? So if I consider like solid only. So when I do the summation, actually expanding to get 12. So that 12 will be the CI, 1 over CI, because in that calculation, CIJ will be 1 over 12, right? So take the inverse of that. So that depends on the crystal structure. So I just, the first one will give me this contribution. And you can see next, if all the A are the same, the cubic current coordinate, I can similarly reduce that. And because the use of the CIJKL or CIJL or CIJLM, that coefficient disappears. Otherwise, I have something extra. So that's why we define this as C's to simplify this expression. So if I just make the notation look clean, I can redefine my A2, right? The coefficient for my quartic terms to be A2. And A2 is simply 1 over Cij times 1 over Sk. So you can do that notation change if you want. If you really keep that 1 over Sk, that's fine. All right. So if I do that, the first can be rewrite something quite similar to the cubic current and quartic. And this kind of bulk energy, right? Or if you divide by the volume, that would be the bulk energy density. Immediately satisfy the constraint that in the liquid it's a minimum 0, and in the solid, in the liquid it's a minimum 0, and it is a minima and with value 0, right? Because when A equals 0, you got the energy 0. You take derivative to show that A equals 0 is equal to 0, which means the minimum. I only have the other two constraints to be fulfilled, which is at solid side. At the solid amplitude, it has to be a minima, and with its free energy also equal to 0, because I have the two minima should have the same height. Okay? That's my double potential I'm trying to construct. So two constraints and two variables to solve, A3 and A4, right? So quickly you can get the A3 and the A4 is associated back to the structure factor and the solid amplitude, right? So you will also need to get this input from your MD simulation. What is where you have a solid, right? From there you can have a time average sense of the density profile and do a Fourier transform that will give you solid amplitude AS. Okay, but with that, we now determine two numbers, just A3 and A4. They are just two numbers. Because A2 is a number, and the solid amplitude is also a number. So, and then we know the A3 and 4. Okay. So we sort of complete the formation of the Ginzburg-Landau theory, right? We're not missing anything, right? So the whole theory looks like this, and A3 and A4 is associated back to A2. And A2 is just a number, so A3 and A4 are just, right? Okay. So to digest a bit of the theory, let me give you one example. It's a 2D hexagonal lattice. But of course, feel free to extend to like BCC calculation. So first, I have to know, or I have to have a reference coordinates, right, to show you where is my K1, K2, K3, etc. So my choice is that it's a 2D system. So my K1 is parallel to the x-axis, and my K2 is 112 degrees away. So in the polar coordinate, theta will be 120, and K3, the theta will be 240. Right? So that's my choice of K1 to 3. And immediately you can see the 4, 5, 6, I choose the same way that 4 and 1, they are opposite to each other, and 2 and 5, they are two the vectors pointing opposite to each other, and 3 and 6, they are also opposite to each other. All right, so that's my choice of my principal resultant vector for the 2D hexagonal lattice. Right? So let's get the number, right? So Cij, clearly, how many combination you can have, just getting two of them to have the sum of k equal to 0. Of course, you can have 1, 4, 6, 3, etc. So you have total 6 kind of way to do that. So Cij is 1 over 6, and Cijl will be 1 over 12, right? So Cijl, which means what? You will need 3 factors getting picking from this configuration and form a closed triangle. So you can do K1 plus K2 plus K3, right? Or plus K1, the second sum, picking up K3, and then the third sum picking up K2, right? Because I'm doing the triple sum here. Okay, the index is from 1 to 6 always. So if I just fixing the first summation, the index is 1, then I have two kinds of choices. So basically I'm saying is I can have A1, A2, A3, or A1, A3, A2, right? So you are fixing the first index, I have two choices. And I can do that for the rest of 6. The next one I can start with A6, something, like A6, then A4, and A5, right? That's the first one. Then I can swap the ordering of 4 and 5. So I can do that 6 times, right? So 6 times 2 gives us 12. So that's why you have this 1 over 12. And of course, I didn't always count this way. I just write a profit. But I mean, it's fun sometimes to get all those coefficients. Right? So let's do one more exercise for triangular lattice, or for triangular lattices. What would be this CIJLM, which means I now pick 4 of them, right? Not written anymore. How many ways I can pick 4 factors? I can repeatedly, I can pick them repeatedly, no problem, because the summation is always from 1 to 6, 1 to 6, 1 to 6, right? So how many kind of combinations I can have? So I'm picking 4 out of, I have 6 retributive factors, I pick 1. And I have a new set, I pick the other one. I have, again, a new set, doing the same thing. So I have those 4 factors, I'm trying to put them together. And how many possibilities I can have in total, so that those 4 factors form a parallelogram in the reasonable space. The answer, of course, I'm showing here is 90, right? But what? Yeah. Oh yeah. So I interpret that yeah. So it's a parallelogram with area 0, basically. Yeah. I also say counting that exactly, right? Okay. So how do we get this number 90? So of course, one of the trivial choices that I can have like K1 plus K4 plus K1 plus K4. Right? So you're adding everything just like Professor Kuo-An Wu was saying. Actually, it's a line, right? So that's one possibility to have to form the summation of 4 factors. The sum will be 0. And how many ways I can form this kind of a combination? And the answer is that just for 1144, you can have a total like 4 factorial divided by, there are 2 repeated index, 11 and 44. So you do this calculation, you got 6. Okay, but that's just 1144, right? You can have like 3 6 pair in here and 2 5 pair here. So total you have 18 contributions and 3. Other than that, you can have really form a parallelogram, right? So you can have like a K1, KC, then K4, and K3. So basically just picking 4 different numbers, and for example like 1 2 4 5, right? 1 2, but if I have a 1, I will need a 4, right? So that will give me I can shift that here so that form this side. And since I have this one, I have to move this 5 to here. So I have this kind of parallelogram. So that's one possibility. So if I invoking like 4 wave numbers to form a closed parallelogram, then how many combinations I'm having? Of course, is 4 factorial, that becomes 4. But how many ways I can pick of those 4 choices? I can have, just like we described, 1, 2, right? And the other just the opposite direction wave number. I can also pick what? I can pick 1, 2, I can pick 1, 3. I can also pick 2, 3, right? So there's also 3 other different kind of choice I can have. So in the end, what I'm having here is 6 times 3 and 24 times 3 and sum them up. That gives me like 90. That's how we did this. Okay. All right. So let us now assume the amplitude, they are real. Of course, by assuming that, we are assuming there is no deformation of my lattices. So locally, all the time, the wave number does not change. even across the interface. And we know that is not always going to be true. But just to form a rather simple theory that is assume that, right? And even if in the very beginning I'm assuming the amplitude they are complex numbers, but since there is no deformation, I can always choose the origin of my coordinate system. I can remove that phase. So here just for very simple case, the amplitude can be just simply to be real. And since the amplitude they are real, then we know the density is the summation of all the plane waves, right? So in order to have the density to be a real number, then A1 and A4, right? They have to be complex conjugate with each other. But since I'm picking them to be real, and there's no choice that A1 has to be equal to A4, and A2 has to be equal to A5, and etc. Okay? And why we need that is just to simplify the calculation. For example, here I should supposed to have like A1, A2, A3, and so many combinations, etc. Right? But total that would be 6. Now the other would be like A4, A5, so A6, and also 6 of them. I am recognizing that 1, 2, 3, and 4, 5, 6 they are the same, so I can just write that simplify. I can express everything in terms of A1, A2, A3. I don't have to invoke like 4, 5, 6. So let's simplify the expression. All right. So for the quartic term, you can do that similarly, right? So I'm just saying the calculation helps me to write down this brief expression. So just saying you have repeated indexes here. So that gives me this 24. And the reason is like A1 equal to A4, so that's the A1 squared. A2 equal to A5, so that's A2 squared. So that's one of the contribution here. But for this A1 squared and A4 squared, since A1 equal to A4, so that becomes my AI to the 4th power. And that should be a combination of 6. That's it. Okay? All right. So hopefully through this exercise, have a feeling that this Gibbs-Landau theory, you can actually get all the coefficients either from the MD or from the MD due to the double well constraint, you can get the corresponding A3 and A4 coefficient. But for the detail of what a term would look like in the free energy, you just do all sort of combinations. So let me even give you one more detail. Is the exact I just write out everything explicitly for you, all right? So, for example, the first term, the quadratic term, I'm summing. I have total 6 possibilities, right? A1 squared, A2 squared to the A6 squared. So here I should write down the A1 squared plus A2 to A6 squared. But since A1, 2, 3 and A4, 5, 6, they are the same, so you have extra factor 2 here. Right? So that's how I did this simplification. And this term is just minus A3 and then times A1, 2, 3. And here I just write out the coordinate expression. So this summation is from 1, 2, 3. So you have this 6 times A1 squared, A1 to the 4th power, etc. A2, A3 here. And for this summation, it's actually a double summation, but I is less than J. So you only have the combination of 1, 2, 1, 3, or 2, 3. And that's it. And for the square gradient term here, since A1 equal to A4, so always you have 2 contributions for A1, for example, right? Because here the A1 dz or the A4 dz are the same. So that's why you don't have this 1/2 refactor here. You only have minus C double K. And sorry, yeah, that's right. So here, if I write down everything explicitly, that should be like K1 dot hat Z squared times the A1 dz squared and plus other 2. Okay. And as I mentioned before, the interface normal dependence coefficient is going to give rise to first a different profile, right? So you can solve that equation, which means what kind of amplitude profile, right? You have the liquid one side, solid one side. So A1 is going to start with solid with certain value and decrease across the interface and reach 0 in liquid. And A2, A3 is going to do the same thing. But they are going to behave differently across the interface because the square gradient coefficient will be different. But the goal is to have those profiles that minimize this free energy. So once you obtain those profiles, you can plug in those profiles back and to evaluate the energy for the interface. That is basically the excess energy, and that's your surface energy. And you can change it to different interface normal, that you can get, again, different results. So in principle, you are expecting to get different surface energy as you change the interface normal. Right? So that's an isotopic free energy for this the Gibbs-Lamont theory. But think about that. Everything comes from the classical density function theory. So the classical theory already predicts that should happen. All right. So let me further make this connection with the phase field so that we can even better. Yeah. Oh, no, that's for liquid. So right at melting temperature, we do a liquid, and we just measure that for liquid. So that's a liquid structure factor. Because the whole density function theory is based on treating solid as inhomogeneous liquid. So the liquid property is very crucial to this interface method. And you only have one field, right? But here I have BCC, I have 12 fields. So I think that makes the fundamental difference. So it's a multivariable phase field. So I think there are several ways we can do this anisotropic surface energy. One is just is a single variable, but you have to play with the density. The other just can open a degree of freedom by introducing more fields, and I can have a greater simplified coefficient. Yeah, something you can think about. Maybe something better or more realistic is lying somewhere in between. Depends on how we try. Yeah, that's good. So just to give you even a better feeling about this approach, let's make the connection with Allen-Kahn equation, for example. Because the equilibrium profile is basically trying to minimize this free energy, right? So we are requesting that it has to be true. The functional derivative of A1, A2, A3 has to be true. And a very natural, that comes later. Let me first talk to you about this. It's just to give you one example or two examples about these square gradient coefficients, right? So that you really have a feeling that's going to be different as the interface normal is changing. So for this hexagonal lattices, let's take the interface normal to be at the x direction, like this one. Right? So for that, the inner product of k1 dot z is parallel. That's going to be 1. And for the other two, you can see for k2 and k3, inner product with z and take a square is going to give me 1/4, right? Because each one will give me negative 1/2. And if I squared that, it's going to give me 1/4. But quickly you will see, if I just change the interface normal to this direction, okay, so here I should have like a hexagonal lattice. So before I was cutting lattice plane saying what's the solid liquid interfacial energy. But the same hexagonal plane, but now I'm cutting horizontally. So I have a solid below and liquid above. So in phase field equation, you already see that the lattice structure in contact with liquid, the atomic structure is already different, right? But so you are expecting the surface energy to be different. But here, I do the same thing. If I just change the interface normal to be in the y direction, you can see those three square gradient coefficient is going to be quite different. You have the 0 and the 3/4 and 3/4. So you have a very good feeling that in the phase field crystal, the larger the coefficient is going to give you a sharper interface, right? So how sharply they are going to change for the 1O interface is going to be quite different if I just change to plot my crystal and in contact my liquid in the 0, 1 direction. But all the density are going to decay, the amplitude are going to decay quite differently into a liquid in this field. Okay? Alright, so let's actually work out the detail and we will end the class today. Okay, so I'm trying to make a connection with Allen-Kahn equation. So since we want to minimize the free energy, one of the natural ways to do it is actually to evolve those amplitudes through the anon concrete, right? It's guaranteed going to minimize the energy. So I just set up some reasonable initial condition, like a hyperbolic tangent profile for the liquid solid. Although I don't know the interface, I can set something arbitrarily. So I just set up for my initial condition, and I simulate 3 coupled anon-count equations. The first one will be partial A1 partial T equal to the negative delta F delta A1. So quickly check, you should have the same result as I did. So take a functional derivative of the whole thing with respect to A1. The first term just gives me 4 divided by S of K times A1. Easy. Next thing, I should have minus A3 times A2A3, right? Minus A3 times A2A3. And for the quartic term, the first one will give me 24 divided by 90. So I still reserve that A4 divided by 90 factor. But here you see I immediately get 24 A1 cubed. And this will be 0, 0. I will have 2 more contributions here. I will have a factor of 48 times A1, A2 squared. That's here. You have 48 times A1, A3 squared. And the square gradient term is going to give me a second derivative and one extra 2 prefactor because this is 2 here, right? And this minus becomes plus. Virtual stuff basically does not change. So similarly, you can write down others, okay? But the concept is what? Is that if you look back the free energy, the bulk term, when we built the Gibbs-Leno theory, the bulk term basically is a double wave potential, right? You have, so what the picture you can have now is that I have 3 variables, so the free energy landscape is going to be 4-dimensional. You have like A1, A2, A3, but when they're equal to all the solid amplitude, it corresponds to a local minimum. When all the amplitude equal to 0, you have the other minima. So it's like a kind of hyper-dimension, but you still have a double wave potential picture in mind, right? Just in higher dimension. And the system is trying to go from A1, A2, A3, they all equal to the solid amplitude and to the liquid. So they are going through this hyperdimension through some paths. They are going to reach from one minima to the other minima. But the efforts they are making to go through that barrier is what? Is the surface energy. So it is exactly like the phase field, right? And you have this square gradient term to penalize the profile changing. So that's how you can have this diffusive or smooth profile. So it is basically multi-variable phase field model. Okay. So what you are seeing here is that I start with something random, and just bear in mind that my K1 is in X direction, K2 is 120 degrees, and A3 corresponds to K in a 240 degrees. And the theta is the interface normal. So in the polar coordinates, my interface now is actually in the y direction, aligned in the y direction. So the normal is in the X direction. All right. So I think that plays quickly. So just focus because the profile reach equilibrium very quickly. Let me just rerun the simulation and focus. What happened in the very beginning? You see the profile changing because trying to minimize the energy. Initially, I was setting all the 3 amplitude. They have the same profile. Very quickly, you will see they spread out. But you will see, oh no, I only see 2, right? You only see 2 colors. You don't see A2. So what is happening here is that my interface normal is in the X direction, and K1 is also in this direction. So the inner product of the K and the interface normal will be 1. So that's you are showing A1. It is merged. That's right. Yeah. Right. That's right. So K23 is here, right? N is here. The inner product is here. But yeah, so it's over. But my concern is that A1 has the largest gradient coefficient. right? Because K dot n is they are parallel. I would think they should have a sharper surface. I have to double check. No? Oh, I'm sorry. It's more diffusive. You're right. Right, because you have the largest coefficient, so you tend to be more diffusive. Otherwise, you're going to have the energy penalty for that. Okay, so it looks all right. So something we are expecting. So let me now break the symmetry, right? Previously, the K2 and K3 with this normal along the x direction are symmetric. So let me break the symmetry and try maybe theta. Try different theta. Let's do it like few degrees, right? So that would break the symmetry. 5 degrees, right? But as expected, still 5 degrees. So you are expecting the largest K dot n is still happens occur with A1. So still the A1 has the most diffusive diffusive interface. But now we break a symmetry, then you can see the A2 and A3 they just differentiate from each other. So you can do the same thing. I think it would be fun to because you have the background with phase field and think about this kind of methodology. And intrinsically, you have this building, or by design, you have this integration method. And so we didn't talk anything about the phase field crystal today, right? But let me give you a preview for tomorrow's class. I'm trying to minimize it. So we only look for equilibrium. So I just give something random in the beginning. I don't have to. Yeah, that's right. What I always found is that it's actually the Anna equation is exactly you don't right, exactly. It's less efforts and you don't encounter too much trouble. Right? So the example I show you is the hexagon lattices, right? But in our 2006 paper, we work out the BCC lattice. So of course here the interface normal is along the 110, right? That's the interface normal. And similarly, although you are expecting 12 density profile, but due to the symmetry, you can divide them into 3 subgroups. So because they have different directional cosine, then you have those different profiles, right? And you can compare with MD results. So yeah, so I'm just picking one of the profile A110 because I have 12, I only pick one of them. And the Gibbs-Lenoir theory is the red line, okay? And the from MD simulation, as I just described, you can do a very careful measurement of the mean density, the time average density, and do a Fourier transform. That's the dots you are having, right? So of course, we are expecting the agreement because we all start the fundamental physics behind. They are all associated with the density function theory of freezing. So does the PFC capture this physics? And the answer is yes, because I'm going to show you tomorrow through the amplitude equation derivation. The prediction from the PFC is actually the blue line. It's actually almost exactly the same thing as the Gibbs-Lenoir theory. Okay, so I think it's about time. Any question? Yeah, that's right. I just switched from just triangle lattice to BCC. This is right. Oh, so yeah, that's right. That's already amplitude, that's right. But there's no guarantee that PFC has any feature associated with the Gibbs-Lenoir or the density function theory. Right? So Gibbs-Lenoir theory itself is fine because by design we're putting those physics. So we are expecting the match. But okay, so in PFC, as you have seen in your simulation, you can also have some kind of solid and liquid coexistence, right? But those are like density waves oscillate. But we are going to derive. Yeah. Oh, so what we are going to do for PFC is actually derive. Okay, so the PFC describes how the psi bar is oscillate, right? But I can also write per side bar as some amplitude times the underlying space. So if I only care about the envelope of the amplitude, so I can make some insight and substitute, plugging everything back into the PFC formulation. And I should be able to get how the amplitude is behaving in PFC. And you will see the extraction basically captures all the previous things. And derive differently, right. So there's no assumption about the liquid structure factor, nothing. Just really start from PFC. But in the end, so let me show you this. We're going to make this connection tomorrow. So that's the amplitude equation you will be getting for PFC, starting from PFC. You will end up with this kind of expression. But you see here, you have this direction cosine dependent again. But there's a reason for that. So we are going to talk about that tomorrow. All right, not happy to end the class. Go for lunch.